Here we are asked to evaluate the given integral, and there are various techniques we can rely upon depending on the form that the integrand takes. We can think about using a basic U substitution to kind of get the problem started. I actually tried that before doing this video and it did not work out. There's no powers of sine and cosine being multiplied, so it's not a trigonometric form. It's not a rational function, so we can't use integration using partial fractions. There's no square root involved, so trigonometric substitution isn't going to work either. The only other technique that we might consider is integration by parts. And so we're going to try that on for size, and what we'll do first is we will let u equal the numerator, so 19 multiplied by the inverse tangent of x. And then dv is going to equal the rest of the expression. So be careful, the x squared's in the denominator, so it would actually be 1 over x squared and then the dx. In fact, since it's 1 over x squared, why don't we do ourselves a favor and just bring that to the numerator. So we can say dv is actually equal to x to the negative 2 dx. Now, when doing the integration by parts, we remember that you have to compute the derivative of your u equation. So you're going to have the derivative of u with respect to x equals 19 multiplied by the derivative of arctangent or inverse tangent of x. We've learned in previous chapters that the derivative of arctangent of x is 1 over 1 plus x squared, and then you'll have a dx here. Of course, in the numerator, we have 19 times 1, so that's just 19. And then for the dv, what we have to do is not the derivative, but rather the opposite, and integrate. So we integrate dv, we get v, and then we integrate using a power rule, we get x to the negative 1, all divided by negative 1. Why don't we rewrite that and say that v is equal to negative x to the negative 1. And then furthermore, let's put the x back in the denominator. So we'll have negative 1 over x to the positive 1. So now that we have our u, our du, our dv, and our v, we can rely upon the integration by parts formula. And we remember that that is equal to uv minus the integral of v du. So here we go. U was 19 inverse tangent of x times v, which we determined was negative 1 over x. Now we're going to multiply this by negative 1 over x. So I guess for now we'll just say negative 1 over x, but then we'll simplify it later. And then minus the integral of that same v, so negative 1 over x times our du. And our du was 19 all over 1 plus x squared dx. Now, as for simplifying, we have 19 times negative 1 right there, so that's just going to be negative 19 inverse tangent of x, and then that will be all divided by x because of that denominator right there. And then here, if we simplify, we have a subtraction of a negative. If we're going to factor that negative out, then essentially we have an addition problem. So we have plus the integral. In fact, why don't we pull the 19 out so we can actually say this is 19. And then what you're left with is just 1 over x times 1 plus x squared dx. So now the challenge is to somehow figure out the value of this integral. And this is more interesting because this actually is a rational function. If we kind of take an aside here, we have 1 over x, and then why don't we rewrite 1 plus x squared as x squared plus 1. We have a rational function that's already factored, so we can use the partial fractions technique. We set this equal to the following. Now, for a linear term, which is just a term in which x is raised to the power of 1, you're going to put a constant over that linear factor. And then you're going to add a different type of numerator here because this is a quadratic factor. So for a quadratic, you're going to include bx plus a constant, and then put that over the quadratic denominator. Okay, our goal now is to find the values of a, b, and c. And to do that, we're going to find a common denominator. So we will multiply this denominator by x squared plus 1, as well as the numerator, of course. And then the other denominator needs an x, so we'll multiply that by x. Once we have the common denominator in this situation, we can just cancel them out. And so this simplifies our lives a little bit. We have 1 equals a times x squared plus 1 plus we'll just do x times bx plus c. Now there's a little bit of a shortcut we can take to find the value of a here. Notice the following. We're going to let x equal 0. And so what that does is it essentially eliminates this term from the equation, because if you plug 0 in for this x right here, you'll have 0 multiplied by bx plus c, which of course is just 0. So we'll have 1 equals a, and then for this x, you're also going to be putting in the 0. So it's 0 squared plus 1. This is an easy equation to solve. We can see that a is indeed equal to 1. So far, so good, but of course we still need to find the values of b and c. And I suppose here we're going to have to go through it the long way. We're going to have to distribute the a and then distribute this x. So we'll kind of come down below here. We'll have 1 equals, well, in fact, a is equal to 1. So we're actually just distributing a 1. And so we're going to have 1 times x squared, which of course is just x squared. Let's not be silly here. And then 1 times 1 is just 1. So x squared plus 1 essentially. And then we have plus bx squared plus cx. Now, what we do is we sort of equate common terms. On the left-hand side, we have 0x squared terms. So we can write that down. And then what that helps us do is set the x squared term on the left equal to the sum of the x squared terms on the right. So basically, you'll have 0x squared is equal to 1x squared plus bx squared. Divide everything by x squared so that they cancel, and you have 0 equals 1 plus b. This shows us that b must equal -1. And then if we look carefully, we need to figure out the value of c. Now this is interesting because on the left-hand side, there's also 0x terms. So we'll do the same kind of thing. We'll take the x term on the left and set that equal to the x term on the right. This one's super easy because then you have 0x equals cx. Divide both sides by x, and you can find out that c is equal to 0. So we have the value of those three constants. Let's go back and see how that will benefit us. So we're going to grab this expression and drag it below here. Right there. And let's clean it up. Let's go back to when the denominators were different from each other. So it would look something like that. And then again, we found out that a was 1, b was -1, and c was 0. So you can rewrite all of this by plugging those in. You'll have 1 over x, and then plus -x plus 0, because c was 0. I don't really like writing plus 0, so we'll just get rid of it, and then that's over x squared plus 1. We can simplify it a little bit. We are adding a negative, so let's just change that to a subtraction sign. And now we have to integrate. Let's not forget that when we were doing our integration by parts, we had to integrate that expression that we had circled. And so now that we have decomposed it using the partial fractions method, we can actually integrate it. So we're going to go ahead and take this expression and we're going to integrate it with respect to x. Now, the first integral is relatively easy. That's just going to be the natural log of the absolute value of x. And then we're going to subtract the integral of x over x squared plus 1. That one, unfortunately, needs to be evaluated using a U substitution. So we're just getting buried in method after method here, unfortunately. But we'll go through with it. We'll set u equal to x squared plus 1. Differentiate, so du is equal to 2x dx. Solve this for dx, so divide both sides by 2x. Then you would have, if we kind of keep ourselves on the side here, you'll have the integral of x over, now your x squared plus 1, we had set that equal to u. Your dx, we had said that that is du over 2x. Notice these x's cancel out. You do have a constant factor of 1/2 that you can place on the outside of the integral, so 1/2 multiplied by the integral of 1 over u du. And this is the same kind of integral, so we're going to have 1/2 natural log absolute value of u. And since u was x squared plus 1, we would have 1/2 ln absolute value of x squared plus 1. That's the integral that's going to go in here. So we'll insert it accordingly. So we finally finished evaluating the integral that was developed while doing the integration by parts. So let's put this all together. These problems require a little bit of bookkeeping, essentially. So we're going to go down here one more time. We will paste what we had going with the integration by parts, but for this integral that we circled, we can now put in its value. So it's going to be 19 multiplied by this expression right here. And there we have the answer to our integral. I suppose we don't really need these brackets anymore, so we can drop those. Maybe put a bracket here, include your constant of integration, and you have yourself the answer to the original integral.